Why does an ice skater spin faster just by pulling in her arms? Nothing is pushing her faster around the circle, yet her rotation speeds up dramatically. The answer is angular momentum, and it is one of the most powerful conservation ideas in rotational motion. In this video, we will define angular momentum, calculate it for the rotating Earth, and then use conservation of angular momentum to explain why a spinning ice skater speeds up when she pulls in her arms. Angular momentum is the rotational version of linear momentum. In linear momentum, momentum depends on mass and velocity. In rotational motion, angular momentum depends on moment of inertia and angular velocity. The equation on this slide tells us that angular momentum equals moment of inertia times angular velocity. Here, the angular momentum tells us how much rotational motion the object has. Moment of inertia measures how difficult it is to change the object's rotation, and angular velocity tells us how fast the object is rotating. Moment of inertia is not just mass. It depends on both mass and how the mass is distributed relative to the axis of rotation. This is why a skater with arms extended has a larger moment of inertia than the same skater with arms pulled in. Angular velocity must be in radians per second when we use the equation in SI units. That detail is important. If angular speed is given in revolutions per second or revolutions per minute, we usually convert it to radians per second before calculating angular momentum or rotational kinetic energy. The SI unit of angular momentum is kilogram meters squared per second. This unit comes from multiplying moment of inertia, measured in kilograms meters squared, by angular velocity, measured in radians per second. The radian is treated as dimensionless in this unit. With the definition in place, we can apply the same idea to a real rotating object, the Earth. The problem asks us to calculate the angular momentum of the Earth by approximating Earth as a solid sphere with uniform density. This is a simplification because the real Earth is not perfectly uniform, but it gives a useful estimate. We are given the radius of the Earth and the mass of the Earth. To calculate angular momentum, we need two quantities, the moment of inertia and the angular velocity. For a solid sphere rotating about its center, the moment of inertia is 2/5 times mass times radius squared. This formula tells us how Earth's mass distribution affects its resistance to rotational change. The angular velocity comes from Earth's rotation period. Since Earth makes one full rotation in about 24 hours, one rotation corresponds to an angle of 2 pi radians, and the time is 24 hours converted into seconds. So the plan is simple. First, find Earth's angular velocity from its period. Then calculate the moment of inertia using the solid sphere model. And finally multiply moment of inertia by angular velocity to get angular momentum. We begin with the period of Earth's rotation. One full rotation takes 24 hours, which is 86,400 seconds. Angular velocity is found by taking one full rotation, which is 2 pi radians, and dividing by the time for one rotation. So the angular velocity omega equals 2 pi radians divided by the period. So this is 2 pi radians divided by 86,400 seconds, and this is equals to 7.272 times 10 to the power minus 5 radians per second. Next, we calculate the moment of inertia. So I equals 2 divided by 5 times m times r squared. And we can substitute the values. So 2 fifths times 5.979 times 10 to the power 24 kilograms times 6.376 times 10 to the power 6 meters squared. And we get 9.7227 times 10 to the power 37 kilograms meter squared. And finally, we can use the equation for angular momentum. So the angular momentum is equals to I omega. So we can substitute the values. I is 9.7227 times 10 to the power 37 kilograms meter squared times omega, which is 7.272 times 10 to the power minus 5 radians per second. And this is equals to 7.07 times 10 to the power 33 kilogram meter squared per second. The key lesson is that angular momentum depends on both spin rate and rotational inertia. Earth spins slowly, but because its moment of inertia is enormous, the angular momentum is also enormous. Now we move to the major idea of this video: conservation of angular momentum. The angular momentum of a system remains constant if the net external torque acting on the system is zero. In simple words, if nothing outside the system causes a twisting effect, the total angular momentum cannot change. This is very similar to conservation of linear momentum. In linear momentum, total momentum is conserved when the net external force is zero. In rotational motion, angular momentum is conserved when the net external torque is zero. The slide states that net torque equals to zero means the system is isolated. Here, isolated means isolated from external torque. Internal forces or internal motion can still occur inside the system, but they cannot change the total angular momentum of the system. For the skater, if we ignore small external torques such as friction with the ice, her angular momentum before pulling in her arms equals her angular momentum after pulling in her arms. So when her spin rate changes, something else must change in the opposite way. That quantity is her moment of inertia. To see how angular momentum can stay constant while speed changes, we need to discuss deformable systems. A system can be isolated from external torque but still be deformable. Deformable means the mass distribution of the system can change. For example, a skater can move her arms inward or outward while spinning. When the mass distribution changes, the moment of inertia changes. But if there is no net external torque, angular momentum must remain constant. So the conservation statement becomes initial moment of inertia times initial angular velocity equals final moment of inertia times final angular velocity. In words, rotational inertia times spin rate before equals rotational inertia times spin rate after. This equation does not say that moment of inertia is constant. It says the product of moment of inertia and angular velocity is constant when net external torque is zero. If the skater pulls her arms inward, her moment of inertia decreases. To keep angular momentum constant, her angular velocity must increase. That is why she spins faster. If she extends her arms outward again, her moment of inertia increases. Her angular velocity then decreases and she spins more slowly. Now we are ready to solve the spinning skater example quantitatively. In this example, we will be applying conservation of angular momentum to a spinning ice skater. The skater initially spins at zero point 0.8 revolutions per second. Her moment of inertia with arms extended is 2.34 kilograms meter squared. After she pulls her arms close to her body, her moment of inertia becomes 0.363 kilogram meter squared. Part A asks for her new angular velocity in revolutions per second. Since no significant external torque acts on the skater, we use conservation of angular momentum. Part B asks for rotational kinetic energy before and after. This is an important point. Angular momentum is conserved, but rotational kinetic energy does not have to stay the same. The skater uses internal energy from her muscles to pull her arms inward, so her rotational kinetic energy can increase. Let us work through the numbers and compare angular momentum conservation with rotational kinetic energy. For part A, we use conservation of angular momentum to find the final spin rate. So the initial angular momentum, I initial times omega equals I final times omega final. And we can rearrange this to find omega final. So omega final is equals to I initial divided by I final times initial angular velocity, and we can substitute the values. Final angular velocity is 2.34 kilograms meter squared divided by 0.363 kilograms meter squared times 0.8 revolutions per second, and we get 5.16 revolutions per second. For part B, we calculate rotational kinetic energy before and after. For rotational kinetic energy, we need angular speed in radians per second. So the initial angular speed, omega, is 0.8 revolutions per second. To convert to radians per second, we can multiply this by conversion factor. 2 pi radians is 1 revolution. And then revolution cancels out, giving us our answer for the initial angular velocity, 5.03 radians per second. And we can convert the final angular speed using the same method. So 5.16 revolutions per second multiplied by 2.5 radians divided by 1 revolution, and revolution cancels out. This is equals to 32.4 radians per second. Now we can calculate the initial rotational kinetic energy, half y initial omega initial square, and we can substitute the values. So half times initial moment of inertia, 2.34 kilograms meter squared, multiplied with initial angular velocity, 5.03 radians per second squared. And we get 29.6 joules. And the final rotational kinetic energy, Ke final rotational, is equals to half I final omega final squared, and we get half times final moment of inertia, 0.363 kilograms meter squared, multiplied with final angular velocity squared, 32.4 radians per second squared. and we get 191 joules. Notice what happened. Angular momentum stayed constant, but rotational kinetic energy increased. This does not violate conservation of energy because the skater did work with her muscles while pulling in her arms. That internal work increased her rotational kinetic energy. So the final message is when external torque is zero, angular momentum is conserved. If the moment of inertia changes, the angular velocity must adjust to keep angular momentum constant.